Hello again, everyone. So, our today's acoustic seminar is dedicated to the topic wave propagation in hierarchical acoustic, porous materials and multiscale acoustic metamaterials. The speaker is Dr. Rodolfo Venegas from Laboratory of Acoustic Phenomena and Matter, Institute of Acoustic, University Austral de Chile. And I kindly ask you to ask questions after the presentation. Yeah, I think, Rodolfo, the stage is yours.
Okay, well, thank you very much, Maria, for the introduction and for the invitation to give this seminar. It's a real honor for me to talk about what we are doing here at our laboratory. And as you mentioned, this talk is about wave propagation in hierarchical porous materials and multiscale acoustic metamaterials, and corresponds to a collaboration with a large number of people, as they are all named here. And the outline of the presentation is as it is shown here. So I'll talk a little bit about our Institute of Acoustics, then what we do in our laboratory, and to then go on to acoustics of rigid frame porous media, which are classical porous materials, so that we get an idea of how do we model them and what the limitations of these materials are. Because those limitations give rise to some of the work we have been doing for quite some time, and that's work to do with triple porosity media, and recently some hierarchical media with distributions of nanopores. And then I'll go into acoustic of multiscale metamaterials of 3 different classes of materials which combine different ideas. And finally, I'll speak about multiscale sorptive metamaterials, which again combine triple porosity media with, let's say, multiscale metamaterials. And finally, I'll speak very briefly about what our work on poroelasticity of nanoporous media to finish off the presentation with some concluding remarks. So at the beginning is very math heavy, and then it will get lighter and lighter towards the end of the presentation. So bear with me, the beginning is math heavy, but then we will be focusing more on results. So we're based in Valdivia, which is a city in the south of Chile, which is, well, Santiago is the capital of Chile, and is here. We are about, let's say, 10 hours drive from Santiago. It's about 900 kilometers. We are at the entrance of the Chilean Patagonia. So all of this thing here is called Chilean Patagonia. And this is our institute, the first floor. And there on the right-hand side can be seen the lab where reverberation chamber is. And this is how our city looks like. So it's a very green city. It's surrounded by rivers. And as you can see, some clouds here that indicates that sometimes it rains, which sometimes means over 300 days a year of rain. So that's why things are kept green as one can see here. So we have an engineering program in acoustics, a master program in acoustics, and recently we have started our doctoral program in engineering science at a faculty level. And in the Institute of Acoustics, we are 8+2 academics with very diverse research interests. Some people work on, let's say, environmental acoustics, other works in soundscapes, and other people work on, let's say, artificial intelligence for acoustics and related applications. And our laboratory itself works on acoustics of materials mainly, but we are focusing on understanding acoustic phenomena in matter in a broad sense. At present, we have 1 research assistant in our laboratory, 2 MSc students, and 3 undergrad students. We have 6 former members. So I'll speak in what follows about what these guys are doing. We have an extended network of collaborators gravitating towards France, but increasingly towards other countries, like, for example, China. And we have been developing projects and publications with them since 2019, which is the year that I came to work at University Austral of Chile. And we're always looking for expanding our collaboration networks. We are very open to discuss ideas and find ways of collaborating. So what's some of the works that we've been doing on multiscale polymorphic media are shown here. So, for example, in this work, we've developed a model for double porosity media. Then triple porosity, I will speak in more detail about this work in particular. Later, we developed some works for acoustics of porous composites, and more recently, poroelasticity of nanoporous media. So I'll speak about this by the end of the presentation. And in terms of research of metamaterials, we have been working on a class of media called permeelastic media, where we have a solid frame and some clamp plates that vibrate at the local scale, and that's determines largely the acoustic behavior of these type of media. So we've developed some work on these permeelastic media, as I mentioned, and then combination of permeelastic media with embedded chemical resonators, and we have recently published a work on double porosity permeelastic media. So let's speak about these works too. Also, we're interested in the effects of inner sources, like for example, heat, mass, or momentum sources that are located locally in porous materials that have multiple scales. So regarding momentum sources, the work of Claudio Parra, one of our students, or our former students, he finished his MSc and now is about to start his PhD in France in the next couple of months. So he did an MSc thesis on wave propagation in permeable media with rotating inclusions. So we have a collection of cylinders, and these cylinders are rotating. And because of the rotation, one can have a very, very different permeability. So we can reduce the permeability by orders of magnitude, and some resonant phenomena appears, or pseudo-resonance phenomena, where convection effects at local scale act as pseudo-elasticity, and that pseudo-elasticity is balanced by the inertia of the fluid itself. And in red is the permeability normalized when these cylinders are not rotated, these immobile cylinders. So by having rotation at the local scale, very different effective properties can appear. So we have recently submitted a paper to to JFM. And Esteban Alarcón has been working on metamaterials inspired by Tesla valves, like these ones. Tesla valves are these devices where the fluid can flow easily in one direction but not in the other one. So we're exploring ways of exploiting that phenomenon to control sound waves in presence of background flow. In this particular example, there is no background flow, but it is the dispersion that we get in this type of devices, arrays. And on the left-hand side here, we have a symmetric Tesla valve and an asymmetric one. And what we can see is that the first band gap is narrower when we increase the asymmetry of the system, and this is the experimental validation compare with sorry experiments compare with simulations, numerical simulation. So he will present this work on next week in the conference Internoise. So Vicente Cuevas is working on bioacoustic characterization of mass timber. So the idea is to implement a complete system for the bioacoustic properties or anisotropic properties of complex materials like wood. So in this example, this is aluminium, a plate of aluminium, and which is isotropic, can be modeled as an isotropic material, and the comparison between FEM measurements where we consider normalized transfer functions are very good. And with a transparently isotropic model, we get a relatively good agreement, but it can be improved for the case of wood. This is a pine, Redetta pine sample. Also, this is to be presented in Internoise. Another student is Cristobal Santos, and he's interested in loudspeakers mainly. So he started developing the idea of using loudspeakers for optimal apparent sound absorption. So here we have the source, and this is the material. This idea has been around for over 60, 70 years. The originality of this is that we came up with a way of finding an analytical solution for the necessary voltage to get optimal sound absorption in a broad frequency range. So as we can see here, with red dots, these are the measurements, and then the red curve is the analytical prediction. This is also to be presented in Internoise next week. And finally, Fabrizio Jarce is working on wave propagation in poroelastic metamaterials. At first, he started implementing all the transport problems that one has to solve to get the effective properties of materials in a software called Phoenix. The idea is to have an open source software so that then we can share all the codes without having to rely on commercial software. And these are, let's say, the validation of his preliminary work, where the sum absorption coefficient is calculated with a commercial software and also with this open source software, and compare with a benchmark that has been published in JSB in 2020. But his project will focus on this on the right hand side. So in blue we have some absorption coefficient of a rigid frame porous material that is very thick, so it's about 10-12 centimeters, and in red is the sum absorption coefficient of these poroelastic elements that are constrained and are arranged as we can see here. So just by rearranging this material and constraining them then locally, we can improve significantly some absorption coefficient with very rich behavior due to inner resonances of these local elements. This is ongoing work, and that is going quite well. So we are very confident that this is going to provide us with a very interesting line of work. So, having said the introduction of our group, now I'll go into the talk itself, and we'll start with these conventional permeable materials, these collections of different type of media, like for example porous materials, which is like solid frame or a solid matrix with perforations. We have fibrous material here, a granular material, and a cellular material, like a classical foam. So all of these materials have in common that we can define a porosity, or the fraction of, let's say, occupied by air in the material, and a characteristic length. In the fibrous materials, the characteristic length will be the fiber radius, and the cells in the cellular material, the cell size, and in the granular material, for example, the grain. So under some circumstances, like for example, we can assume that the motion of the frame is negligible. And if we have scale separation, meaning that these characteristic sizes are much, much smaller than either the wavelength of the sound that is going to propagate through the material, or the sample size, let's say the thickness of a layer of a foam, then we can model these materials as effective fluids or equivalent fluids. It's we use these words for the same purpose. So in order to justify that, we use a method of homogenization that is called two-scale asymptotic method of homogenization. The objective is to derive an equivalent macroscopic model that encapsulates the local physics through effective parameters. So this method relies on the separation of scales, which is what I've just mentioned, that the local characteristic size over a macroscopic characteristic size should be much smaller than 1. So it should be equal to epsilon, and this epsilon is a very small parameter. And the steps of the methods are the 7 steps that are shown here. So first, we formulate the local description, the local equations that govern the physics of a problem. We do a physical analysis, and through this physical analysis, we work out the relative or order of magnitude among the terms involved in the equations. We introduce 2 spatial variables, one accounting for macroscopic variations like x, and y accounting for local fluctuations. And we rescale the local description to then use asymptotic expansions or ansatz, that's where we say this variable is a series of in powers of epsilon, and identify local problems where we can solve them, and from the solution we get the effective parameters of the medium, and finally we derive the macroscopic equations that govern the phenomena that we're interested at the local scale, but macroscopically. So these are 2 excellent books on the subject. I would recommend this. The book by Sanchez Palencia is, let's say, more mathematically oriented, while the book by Oriol, Boutin, Lange, and Roy is more focused on the mechanics. These are the approaches are different, but the subject is the same. So let us rationalize this by considering a microscopic scale. And if we zoom in, we get this microscopic scale and a representative elementary volume, which is composed of a solid frame in black, let's say a pore space in white, we call it omega f, and gamma is the interface between the solid part and this fluid part, and n is a normal vector. So we consider scale separation. So this characteristic size is much smaller than this macroscopic characteristic size. We consider also that the material is periodic for simplicity, and the frame is motionless. So the vibration or the propagation of waves through the solid part of the material is negligible, either because the solid part is much heavier than the fluid one, or is more rigid than the fluid part. So to illustrate the separation of scales, let us consider, let's say, granular material, consolidated granular material with a characteristic size of 1 millimeter. So 1 millimeter grains that are sort of fused together. And if we were interested in understanding how a wave of 100 hertz propagate here, we can see that the separation of scales is satisfied because the wavelength is in the order of 3 meters and the characteristic size is 1 millimeter. So we can apply these methods, and the description that we will see will be applicable to this case. So what are these descriptions? Well, we start with formulating the local equations, and in particular, we formulate 3 equations of conservation, one of the momentum, which is given by this Stokes equation here, conservation of mass, conservation of energy, and we have basically 4 variables: the fluid velocity, the pressure, the acoustic density, and the temperature. So we need a 4th equation to close the system, and for that we use the equation of states that is shown here. And also we have to formulate the boundary conditions on gamma, and those are of 0 velocity and 0 temperature excess. This doesn't mean the absolute temperature or thermodynamic temperature is 0, but rather just the oscillatory part of the temperature is 0, because the thermal impedance of the solid part is highly contrasted with respect to the thermal impedance of the fluid that saturates the material. So then we analyze the physics. So we see that the flow is driven by a macroscopic pressure gradient. So an estimation of this macroscopic pressure gradient is PC, being C descriptor of a characteristic value of the variable it is applied to. So PC is a characteristic value of the acoustic pressure, and L is the macroscopic characteristic length. Also, the fluid velocity and its rate of deviatory deformation fluctuate locally, so we can estimate this term in this way. And we're interested in the case where all the terms in the Stokes equations are of the same order of magnitude, so that we can capture viscoinertial effects. Using that, then we introduce these 2 adimensional, in this case, spatial variables, accounting for slow variations and fast variation. Now, a priori, every variable is a function of these 2 spatial variables, and that has as a consequence, because these are independent variables, where we can write the gradient operator in this way. It becomes essentially a function of 2 variables, so we use this for the Nabla operator. And insert this, adimensionalize this Stokes equation, and we identify that this term is in the order of L squared, and that's divided by big L squared, so that's in the order of epsilon squared, and this is what appears here as a ray scale local equation of conservation of momentum. The divergence doesn't change locally, but rather macroscopically, and therefore there is no scaling here. And for the temperature, we have for this a conduction term, we have an epsilon square of rescaling. So then we say that every variable is a series in terms of the epsilon. It's a power series in terms of epsilon. For example, pressure is equal to the leading order pressure, which is P0, plus epsilon times the corrector of pressure, and so on. We insert this series into this equation, and we then identify the terms of different powers of epsilon. So at epsilon minus 1, we get that the gradient with respect to the local variable of the leading order pressure is equal to 0, which means that the leading order pressure doesn't depend on y, but rather just on x, which is the macroscopic variable. Here I have to say that we have used a little bit the notation because we got rid of all these stars, indicating that this is adimensional, but this is just a conventional way of doing it so that the notation doesn't get too clumsy. So if we keep the identification process, we identify the oscillatory Stokes problem, which is this one here, and a heat conduction problem or Fourier problem. And this shows that the oscillatory flow is driven by the macroscopic pressure gradient, and this is a linear problem, so that we can write the solution as an operator, in this case K, with this bar, acting on the external force. And in the same way, for the Fourier problem, we can write that the temperature is an operator acting on the force in turn. So those are the, let's say, abstract solutions of these two problems that we will use later to get the macroscopic description and a way of calculating effective parameters. But before that, we identify at epsilon 0 what happens for the equation of conservation of mass, and we take the spatial average defined by these brackets in this way. With respect to omega f, this is the porous space, and omega is the volume of the representative elementary volume. And in particular, this source term becomes equal to 0 because the velocity is equal to 0 on gamma. And this is important because later when we will see other problems, this is not going to be the case. This source term will help us to link the multiscale phenomenon. So for this term, we can do a little bit of algebra and write it in this way and define the compressibility as it is shown here, which depends on the dynamic thermal permeability, which is the spatial average of this local operator here. So what we do is to say P naught is equal to 1. We solve the problem for temperature. Since we know P naught, we solve for the temperature, and we know the rest of the parameters. We know the local operator here. We take the average, and then we get the dynamic thermal permeability. And in a similar way, we take this solution, we take the spatial average, and we get this Darcy's law, where K is the dynamic viscous permeability and is the average of this local operator. So that's the conventional porous materials. So the properties, if we consider, let's say, isotropic media, because this is in general is a tensor, a second rank tensor. So if we consider a particular flow direction or that the material is isotropic, we get that the dynamic viscous permeability becomes a scalar, and this scalar permeability tends to its, let's say, keynote value, which is the value for when frequency tends to 0. And at high frequencies, it tends to a purely imaginary value shown by this, where delta V is the viscous boundary layer and alpha infinite is the tortuosity. So the transition between these two regimes is given by this Biot characteristic frequency, and phi is the porosity, it is the dynamic viscosity, rho naught is the equilibrium density. And for frequencies much smaller than this Biot frequency, we get that the permeability tends to its static value, and we will say that this is determined by the viscosity of the fluid. So we're a viscous dominated flow regime, and for frequency much larger than higher, than the Biot characteristic frequency, we are in inertia dominated flow regime. The imaginary part, minus the imaginary part, has got a peak around the Biot characteristic frequency, indicating that this is where the sound energy dissipation is maximum. In a similar way, we have these are the low frequency and high frequency limits of the compressibility. And around this thermal characteristic frequency, you have a small peak in the imaginary part that shows that the dissipation of energy due to heat conduction is maximum around this characteristic frequency, which is the thermal characteristic frequency. So below this thermal characteristic frequency, we are in isothermal regime, and above, well above, we are in adiabatic regime. So these are the classical, let's say this is the classical behavior of the dynamic viscous permeability, and this is the classical behavior of the effective compressibility. We will see that in more complex materials with different physics, the behavior of these two effective parameters will change significantly, and that will help us to control sound waves in different ways. So let us start with, well, summarize this idea. Viscothermal dissipation in these single porosity materials are due to gas viscosity and thermal exchanges between the fluid and the solid frame. So the porous scale physics are the linearized equation of conservation of momentum, mass, energy, and of state with boundary conditions of no slip and null temperature variation. We applied homogenization and we get this effective fluid description where this is an effective mass balance equation and this is the fluid flow constitutive law. And these two parameters are the effective parameters of the medium, the effective compressibility and dynamic permeability. We can then relate the dynamic permeability to what it is normally called dynamic density, as we will see later. So, though this is well known, and the question is, what can we do to change this or get different properties of these effective parameters? So with that, we will start talking about hierarchical permeable materials. And we understand by that a permeable material with several well-separated characteristic lengths, like for example, this structural zeolite, where we have, let's say, heterogeneities at the very nano scale, and this is a 20 nanometer scale. And here we have, let's say, 1 micrometer pore. These materials may come in granular form, so we have the size of the grains, and that's another characteristic length. So we have at least 3 scales of porosity here, one related at the nanoscale, microscale, and then mesoscale around these grains. With aerogels, it's a similar picture, but we have focused on investigating activated carbons for quite some time. This is a particle of activated carbon, and these are SEM images of the surface of these particles. So we have very, let's say, lots of pores that are in the order of 1 micrometer on the surface of these particles, and some of them are even larger, like let's say 5, 6 micrometers across. So we can think of activated carbon as a material with a triple porosity, where we have a macroscopic scale, one porosity associated with what's happening around these grains. The grains are in black. So inside these grains, we can make a zoom in and we can see these micrometric pores. And let's say on the walls of these micrometric pores, we have nanopores like this. So essentially, this is the stuff in black here. These pores are what is in white here. And then we don't have TM images, but these materials do have nanopores, and this is the representation of them. So we consider a single type of nanopores. So what do we do is to consider again a periodical hierarchical material, and there's scale separation. So this is in the order of 1 nanometer, this is in the order of 1 micrometer, this is in the order of 1 millimeter. So this is 1,000 times larger than this is 1,000 times larger than that. And we consider long wavelength wave propagation and applied homogenization from this scale to get a representation of what's happening in the grains itself. And then we couple that representation with the Fourier-Stokes system formulated around these grains, and we applied again homogenization to get a macroscopic description of wave propagation in this medium. We will see that some energy dissipation is due to classical viscothermal dissipation at different scales, pressure diffusion affected by sorption and rarefaction. Rarefaction is a phenomenon that appears in pores that are compatible with the mean free molecular path, and mass diffusion affected by sorption, which is the process whereby these molecules are transported from these pores into these nanopores. And sorption is a process that will stop a little bit to talk in more detail here. So first, well, mass diffusion, just to remind, is a flux of molecules from a region of higher concentration to one of lower concentration, and generally has a slow characteristic time in comparison with what happens at sorption. Sorption is a term that we use for the denominate adsorption and desorption. So adsorption is the adhesion of fluid molecules onto the surface, as we can see here with these black circles. Desorption is the inverse phenomenon. So these molecules get released off the surface and are in the bulk of these small pores, as shown in these white circles here. And this has a fast characteristic time. So the residence time of these molecules on this surface is pretty small. So how do we model this? Then we consider mass flux related to a diffusion coefficient for the molecules that are in the bulk of the pores with a concentration Cm, and also another mechanism of diffusion, then in this case the surface diffusion, of the molecules that are absorbed with a concentration Ca. We could carry out a mass balance of divergence of the mass flux is balanced by this effective concentration, and we relate the concentration of the absorbed molecules with the concentration of the free molecules through a local isotherms of linear type, with H is the linearity constant. We insert this equation here, and we can write all of this in terms of densities instead of concentration to get to write to this equation where D is an effective diffusion coefficient that has two components. One is weighted by this bar phi, which is the volume fraction available for transport of free molecules. One minus the phi is the volume fraction available for the transport of adsorbed molecules. This option, sorry, diffusion coefficient is weighted also multiplied by this H constant that is relating the concentrations. HE is called a linearized effective equilibrium constant, and appears multiplying the density profile in this equation. So we formulate the Fourier-Stokes equation just as previously for what's happening around this domain. And we formulate equation of continuity of mass flux, continuity of density, continuity of temperature jump condition, because we are considering let's say rarefaction effects. And in the nanopore sorptive domain, which is essentially this part, we formulate this diffusion equation, and we carry out homogenization to get, let's say, the first order. Then we get this oscillatory Stokes problem with a slip boundary condition, and then we get a heat transfer problem considering this temperature jump condition on the interface, and we get this oscillatory mass diffusion problem with the density being forced on this interface gamma, this one here. So these three problems are, one of them is forced by the macroscopic pressure gradient, this one is forced by this, and this one is forced by this constant density here. So we can write the solutions in terms of operators acting on these forcing terms in this way. And after that, we work out the macroscopic description from the equation of conservation of mass, where in this case now the source S is no longer zero as in the previous case, but rather is related to the mass flux. And this term here, if we apply the divergence theorem, we can use this equation, we get the Laplacian of this, and then that we relate that to this term here to get this expression here. So this is J omega HE multiplied by the average of the density, local density field over, in this case, the equilibrium density. So we can write the mass balance just in a classical, similar to the classical way, with the difference that the permeability is affected now by rarefaction effects, and the compressibility has two components. One of them coming from the micropores, and another component coming from the nanopores, and this mass diffusion that occurs in between these two domains. And this is the expression for the compressibility, and the compressibility of the nanopores is this linearized optional equilibrium constant over the equilibrium pressure, and F takes the classical form of a relaxation function if we were to consider this in time domain. So this was published in this work, and we use this formulation to couple it with the Fourier-Stokes system now formulated on this omega PF pores. What we have just derived here is formulated in the grain. And this is shown here. And the boundary conditions between these pores and these grains on gamma p are continuity of mass flux and continuity of pressure and temperature. In particular, as previously, this is showing that the mass flux generated or pulse from the macro for this porous grain is much smaller than the mass flux generated by the carrying way around these grains in these pores. We solve the problem, and because we get very similar results, very similar problems, Stokes problems, and then Fourier's problem, and when we identify the mass balance equation at the linear order, we take the average, we end up with this description that is also of an effective fluid, where the permeabilities determined purely by the permeability of what's happening around the grains. But the compressibility has one component coming from this part here around the grains, plus the compressibility of the grains itself, this CMN, and this pressure diffusion function that is accounting for the multiscale or interscale coupling. So the general form, now we have already seen that CMM takes this form, and this is the general model that we have published in Physics of Fluids in 2017. In terms of results, the normalized effective compressibility is largely affected by this sorption phenomenon. So if we do an asymptotic analysis at low frequencies, we see that depends on HE. And for a triple porosity material with sorption, the compressibility is very large. So sorption increases the real part of the compressibility in comparison with, let's say, a triple porosity with no sorption or other materials like as shown here. Also, when we look at the imaginary part, we have different peaks now, and these peaks are related, one to pressure diffusion, another to heat conduction around the grains, and another one to mass diffusion. So what sorption does is to enhance the dissipation and also slow down some of these, let's say, diffusion processes. So we, instead of having a peak at higher frequencies, absorption makes them go into lower frequencies. And that is very convenient because we can see that the effective speed of sound is real part is well predicted by the model, and in terms of, and that's a comparison with measurements, and is much slower than the effective speed of sound in a material with, let's say, grains that are completely solid, a single porosity material with no absorption, as shown here, and that translates onto the attenuation coefficient. So the attenuation coefficient at low frequencies is much higher for a triple porosity sorptive material, and this is the experimental validation. In terms of sum absorption, which is a parameter that indicates that if it is equal to 1, all the sound energy is absorbed by the material, and if it is equal to 0, it means that all the energy is reflected back. When we consider this material placed on a rigid surface, we can see that the sum absorption coefficient is very high at low frequencies. If we compare it, for example, with a material with solid grains, like shown in gray here. So this is a remarkable high sum absorption for such a thin layer of 3 centimeters. We have applied the same model, but for other type of multiscale materials like aerogels, showing good agreement. And what we have been recently doing on this is to incorporate the effect of bimodal nanopore size distribution. So carbon materials tend to naturally have a bimodal nanopore size distribution. Some time ago, when we started this, we looked at these 2 peaks and say, well, 0.5 nanometers is very similar to 1.5 nanometers, so we will consider a single nanopore size. That's been proven a good approximation for many materials, but for others that might not be the case. And this is another example of the bimodal nature of the nanopore size distribution of carbonaceous materials. So the idea is to consider 2 types of nanoporous patches two types with different types of nanopores, let's say one with larger nanopores and the other ones with smaller nanopores, just like we're considering here, smaller nanopores, larger nanopores, or in blue here and blue there, so it's about 1 nanometer and 10 nanometers. And we applied the same methodology. The difference is that here we end up with a couple mass diffusion problem affected by sorptive, and this is the couple diffusion mass diffusion problem. So this is formulated in one of the nanoporous patches. This is formulated in another one. On the boundaries that are, let's say, in contact with the surrounding fluid, we formulate this forcing condition here of a constant density forcing this local density field. And in the interface between these patches, we have continuity of mass flux and continuity of density. So the general model is very similar. In blue is what it is different, but the difference is that a summatory appears here, accounting for what's happening in these nanoporous patches. And this F function is defined in a very similar way than previously, but from the solution of this couple problem instead of just a single mass diffusion equation that governs the problem. So if we look at what happens at low frequencies, this depends again on the linearized sorptive effective equilibrium constant related to each nanoporous patch that can be related to the Langmuir model in this way. That gives us a way of estimating some of the parameters with non-acoustic measurements, like for example, using the value directly of the nanopore size distribution that is measured using absorption isotherms and then some post-processing with specific models to get this type of data. This is what we're working now at. But for now, I'll give an example of one particular geometry. So this is a micrometric pore, and one nanoporous patch is omega n1, and the other one is in blue. So, and we formulate this and solve this problem numerically to get this type of results with these local density fields. In particular, this means that at low frequencies, this nanoporous patch 1 is all contributing to the mass diffusion through this nanoporous domain, while the other nanoporous patch has a constant density, and at higher frequencies the opposite. So this nanoporous patch is contributing with, let's say, a locally varying density field, while in this other nanoporous patch, everything is confined to this mass diffusion boundary layer, so it's not contributing to the behavior. But what we can do by changing the nanopore size and therefore the linearized equilibrium constant, sorption equilibrium constant, and diffusion coefficients is that in one of these mass diffusion functions, we'll have a peak related to dissipation of sound energy at low frequencies, and the other one at much higher frequencies. So we can use that to tailor the response and affect low frequencies with one type of nanopores and high frequencies with a larger type of nanopores. This is an example of normalized compressibility that, despite the fact that it doesn't look very different, it does have some difference when we look at the sum absorption coefficient. So in blue, we have a bimodal nanopore size distribution, and B is another bimodal nanopore size distribution. And in black and gray, we have the respective materials with unimodal size distribution, with in particular the small nanopores in black and higher larger nanopores in gray. So we can see that the smaller nanopores are affecting low frequencies, while the larger nanopores are affecting higher frequencies, the sum absorption at higher frequencies, and the bimodal case is somewhere in between the unimodal ones. But here it's very close. So this is clear that the smaller nanopores are beneficial to improve sum absorption at low frequencies. So those are to do with, those are to do with, those works are to do with multiscale porous materials or hierarchical porous material with sorption that is affecting significantly the behavior of acoustic behavior of this kind of media. Now I'll move on to a multiscale permeoelastic materials or metamaterials. And here the hypothesis is that by locally constraining these plates, we will have local fluid structure interaction, and that local fluid structure interaction will modify the permeability of the medium rather than the compressibility. So we formulate the local equations, which are the conservation of momentum, conservation of mass, and on these boundaries that are solid of rigid frame, the velocity is zero, but on the plate we have continuity of velocity, or sorry, the velocity of the fluid is equal to the normal velocity of the plate. And here we have the conservation of momentum for the plate that is loaded by the difference between stress on both sides. And again, and this is the rest of the constitutive equations of the plate, and the boundary conditions indicating that the plate is clamped on these edges. So the physics is pressure wave will generate a velocity field, this velocity, and also a stress field. The stress will set these plates in motion through this term here, and when these plates move, they will affect back the fluid flow in this case. So we get local fluid structure interaction problem whose variational or weak formulation is shown here. So these two terms are the traditional terms related to viscosity and inertia of the fluid, but the presence of these films make these two terms appear. One of them is to do with the inertia of the films or the plates, and the other one is to do with the elasticity. So when the elasticity is compensated by the inertia of the fluid's plate system, we will see resonances. And again, this problem is linear, forced by the macroscopic pressure gradient, so we can write the solution as an operator acting on this external forcing term. The macroscopic description is of the same type of previously, but in this case, the dynamic viscous permeability becomes a bit more complicated because it's the effective dynamic viscoelastoinertial permeability. And we can define the dynamic density in a classical way through this expression here. And we can show what happens in a prototype material to exemplify the effects of these resonances in particular. And in this case, this is, let's say, a little drum with one plate on one side and is open on the other side, and it's an array of them. So they have this is a perfectly rigid solid frame. This is the fluid, and in red is the film or plate. So at low frequencies, the material with flexible films behave just like the material if these films were perfectly rigid. But at a frequency F0, we have this is the anti-resonance. We have that the magnitude of the permeability is very small, while at the resonance frequency is much higher. And then at higher frequencies, it will tend to the classical case, but this pattern will repeat. This pattern will repeat. So then this is what happened here at this point. So the flow is very high here and it goes in this direction here due to the vibration, and around this gap it goes in the other direction. So when we take the average, it goes to zero in practice, and that explains the minimum. And this is in the maximum, the flow is pretty much driven by the vibration of the plates. So in between these two characteristic frequencies, we have a negative effective density. Above this resonance frequency, supersonic velocity and a phase shift. And this is the experimental validation where we can see that there is a phase shift related to the resonances of these small plates. So for acoustics, array of acoustic resonators, we have an array of Helmholtz resonators. We apply homogenization, and we get that the compressibility is affected by the admittance of this acoustic resonator. And that will lead to, let's say, in blue is the compressibility associated with what's around this resonator, and in red is the compressibility associated with this resonator itself. So, and black is the combination of both. And the imaginary part, we have a relatively large peak at the imaginary part around the resonant frequency of the resonator, and this is the compressibility of the combined, the overall compressibility. When we combine permeelastic media with embedded chemical resonators, we can see very interesting phenomenon. We can match the resonant frequency associated with the chemical resonator with the resonant frequency associated with plates, and below this frequency we have the real part of the effective density is negative, and the real part of the compressibility is negative above this frequency. At very low frequencies we have that the wave is diffusive and slow, and it's very, very slow, and then it's overdamped and slow. It becomes regressive when this at the frequency where these two frequencies are matched, and then it's overdamped and slow again, diffusive and supersonic and weakly attenuated in above this characteristic frequency. So it's a very rich phenomenon. This is just an example of many possible behaviors that can be seen in this type of media, and I would invite you to check out this paper for more details. Then if we, instead of having a resonator, chemical resonator, we have porous material with highly contrasted permeability, we have a media called now double porosity permeelastic material. In this particular case, there is a typical density where that we will see, and this is a part of a work that we have recently published in this journal. And an example of the speed of sound is this one. There's the reduction in speed of sound, and then a very sharp increase in speed of sound leading to supersonic velocities. And pressure diffusion, in particular, when we match the anti-resonance of the plates and the characteristic frequency of pressure diffusion, induces regressive waves in between these two characteristic frequencies. Without accounting for that, we wouldn't see this, we wouldn't predict these regressive waves. Now, instead of having, let's say, plate that doesn't actually make this fluid phase disconnected, we can create this, disconnect this fluid phase by creating a cavity that is closed by this plate in this way. So in that case, now we have an atypical compressibility. It's no longer an atypical permeability or dynamic density, and the effect can be seen here. So if we have a double porosity permeelastic material, the speed of sound, the magnitude is bounded, as shown here by this expression that depends on the imaginary part of this pressure diffusion function, and we have higher attenuation pretty much in the whole frequency range. Now we have, imagine we have, let's say, a perforated phone where we place a tube in it, and within the tube there are some plates that disconnect this fluid phase. In this case, we have an atypical density, and the speed of sound behaves in a rather particular manner. It starts increasing and it goes like this. It becomes supersonic at the resonance frequency of the plate. There's no anti-resonance frequency here, as we've seen in this particular case. So it goes directly to a maximum, but without having a minimum. So that's a very unconventional behavior that can be exploited for weight control applications. So finally, multiscale sorptive metamaterials. This is a paper we've submitted recently, and it's a combination of activated carbons with some resonators with foams in it. So this is a realization of the sample, and here we can see that the analytical model and numerical model gives very similar results than the measured ones. So there's a good agreement between the analytical numerical model, and the multiscale material exploits several sound energy dissipation mechanisms. So our work related to molecular and microscopic model, I will skip a few slides just to give an idea. The idea is to simulate and solve these problems, dynamic molecular dynamics, to estimate the elastic parameters of this zeolite structure. And we used 3 different routes. One of them is a statistical physics route. that is basically related to the fitting of the dynamic structural factor, a mechanical route that mimics a mechanical test route that mimics the molecular dynamic classical extension and compression test, and a strength fluctuation route based on the work of Parinello and Raman, where from the strength fluctuations we work out the mechanical properties of these materials. So we use that, and then we use this as input to a model based on homogenization for a double porosity poroelastic material. So we have carry out the homogenization, and then we use these molecular dynamics parameters to input as inputs of this macro-scale model for double porosity poroelastic media to work out the, let's say, normalized laminar parameters or Young models, and see how the volume fraction of this of these consolidated grains changes the overall mechanical properties of the materials. And these are the normalized velocities. So we've done similar things with chemoelasticity, and I'll skip this, and just to say that what we're working on is to work out this double porosity description for poroelastic media, where all these terms in red are calculated from molecular dynamic simulations, thereby linking molecular scale phenomenon to macro scale acoustics behavior. So we have presented some of our research on wave propagation in hierarchical porous materials and multiscale acoustic metamaterials. And this very briefly presented this nano to macro modeling strategy for poroelastic media. And the key takeaway is that the sound dissipation in this complex media is determined by a number of physical phenomena, and we can exploit these phenomena to improve or manipulate and control waves in general. So what we're doing now is to work on wood, CLT. We're trying to model this type of complicated structure, and also we are investigating different physics and multi-scale materials like aeroacoustics, thermoacoustics, chemiacoustics, and we're carrying out experimental work. So we have to thank, obviously, our funders. We're grateful to have knowledge and support from this Chilean Agency for Research and Development through these two projects. And thank you very much for your attention, and your questions and comments are very welcome.
Thank you. Thank you for the presentation. Dear colleagues, please ask questions in Zoom or in Jupyter.
I see some question in chat of Zoom, and yes, of course, we can share our recording of Professor if you send our contacts to here in chat, or to Maria, or I don't know, some of us. Later, maybe I give you our contacts of our laboratory email. Okay, sorry.
Yeah. I'm happy to do so.
Okay, I can send the recording of the presentation to the email. Thank you. So, guys, please, questions? Any other questions?
Okay, maybe I have some question regarding the beginning of the presentation, where was absorber and the measurement in tube of absorber.
Am I still sharing the presentation?
Yeah,
right?
we can see it. Yes,
you can see it here. Okay. So I don't know what I did. Yeah, there we go. Yeah. So you were probably asking about this?
yes. Actually, I was wondering what So this absorber it's a kind of a bulk porous media, yes? And what is the thickness of it?
Yeah, but this is a good question. I didn't explain it properly, actually. So this is the source of our impedance tube, and we use this box, loudspeaker box, as a material. So what we have done is to work out a way to know the voltage that we should send this to this material, which is a loudspeaker box, in order to achieve this optimal sum absorption. What we're doing now is to combine this with, for example, putting some other materials like foams or resonators, so that we can have an hybrid material where if the loudspeaker is not working, then it's a passive material where you have a foam backed by a membrane resonator with a large cavity. But also we can try to, in some frequencies, use it and use this loudspeaker box emitting sound so that we can control the sound absorption in particular frequency range. So this is what we've been doing with this. So in summary, just to answer straight away your question, the material is the loudspeaker box. There's no foam or anything like it here. It's just this loudspeaker acting as a material. Mhm.
Okay, thank you.
Thank you for the question.
So any other questions, please? May I ask some questions about the last few slides of your presentation?
Yeah.
You did some numerical simulations, and were in console or your own code with your own code?
Yeah. In this one, these simulations were done with a software called LAMS. It's large atomic multi-parallel or something. It is called, and it's a well-established open source software that is one of the many that are used for this type of simulation. So these simulations were done by our colleagues in Grenoble. In particular, we have this Alan Sam is a joint postdoc. He did some work in Grenoble and then came to work with us in Valdivia. And so they did these simulations with this software called LAMS. And then these other simulations, which are, let's say, the solutions of this boundary value problem in particular, those were done with commercial software, which is COMSOL Multiphysics. And using that software, we could work out this effective elasticity tensor, and then all of these parameters that then give us this curve here. So it's a combination of both LAMS and also COMSOL Multiphysics. And related to that, Fabricio Ojars is working on, let's say, trying to do all these codes instead of in doing them in COMSOL. He's trying to implement that. Well, not trying. He's doing it actually. This is the proof. He's implementing all these boundary value problems in this software called Phoenix, including fluid structure interaction problems and what we see in here. Those are basically the software we use at the moment. So LAMS, COMSOL, and Phoenix to do all the numerical calculations.
Okay, thank you. And measurements were provided in the impedance tube, which were shown in the first in the beginning.
Yes, I think. Well, yes, no, yes, most of them, yes, because we have implemented. Where is it? Sorry, we have two impedance tubes in the lab now. One of them is the one shown here, and this works up to, let's say, around 1600 hertz from 200 hertz up to 1600 hertz. And we also have implemented, I think I've got another one here to show. That's, but where is it? A smaller impedance tube. I'll find it. There we go. So this small impedance tube in diameter is about 34 millimeter diameter, and that's for higher frequencies. And this works currently from about 400 hertz, at least 400 hertz, up to 5,500 hertz. So those are, but yeah.
Okay, thank you.
Mhm.
Any other questions?
Yeah, if I may.
Yeah, hello, Elena. Please.
Hi, Maria. Hi, Rodolfo. Thank you very
Hi,
much.
Elena.
It's super interesting. Just a bit naive about the material where you showed the chemical structure. How does this
Mhm.
material look like? Is it like a foam-looking thing, or what is it?
Yes, I'll essentially this is the, let's say, the molecular structure of zeolite, and here we go. Yes, so this is like, say, the at the very molecular scale how this looks like, and it's composed of silicate, and this is the composition here. So it's got silicate, oxygen, and silicate, and a lot of different bonds that are shown in different colors. And then that's sort of the substrate of the material. So, but normally these things are like powder-like. So that's why we consider this type of structure. So we say that, okay, these powders are, let's say, consolidated, and with this consolidated, you make sort of pellets, and these pellets or can be done also in type of a spherical way, and then you can sort of sinter them to work out to get something like this. But normally, these type of zeolites are in, let's say, in powdered form, but nothing impedes to have them in different forms. Like, for example, with activated carbons, you can have them in granular form, pellet form, powder form, or even fibers. Activated carbon fibers are also available. So for zeolites, I'm aware of I'm not aware of, let's say, a fibrous material made out of zeolite, but in principle, I guess it could be possible.
So it's not a periodic structure, or is it?
Oh, no, none of them are periodic, but we have to assume that they are periodic so that our life is a little bit
Okay.
easier. No, I mean, most of them are, I mean, well, the zeolite itself, this is, let's say, the structure at the molecular scale looks like this, and it can be considered kind of, let's say, pseudo-periodic. Well, it is periodic in this simulation, but in reality, I think it will be close to periodic. But then, as soon as you start like scaling this thing up, so then we have, let's say, for example, defects in fabrication, and that creates like microfractures or anything, and that breaks every sort of periodicity and randomness. But the good thing is that it has been shown that, for example, in terms of let's say this macroscopic description, whether you start on assuming that the material is periodic at the local scale or random, you end up with the same type of macroscopic equation. The only difference is that when the material is random, you don't really have a specific, an easy way to identify a representative elementary volume. So you have to kind of say, okay, this representative elementary volume is this, and then you make simulations, and then you create another one, and then you start sort of combining them using, let's say, a different ensemble average to work out the effective properties. With a periodic material, you just have this ref that is well defined. You solve it in there, and you get just your effective properties. So that's kind of the main difference. So in one case, you've got a very well established geometry where you solve the problem, and in the other one, you have to do many realizations and then work out its effective properties.
So that means it doesn't matter if it's periodic or not, you will not get any anisotropic effects.
I think it will matter in the sense that I think let's say certainly the isotropy characteristics will be different for for what we've seen When you have, let's say, materials that tend to be random, they tend to be, let's say, more isotropic somehow. But that's in practice. It's in terms of modeling. Sometimes the differences are not that huge. If the let's say the standard deviation is not too high, obviously. So if let's say you have a one type of material with a unimodal pore distribution with just one type of pore, and if you have the let's say permeability of that in comparison with the permeability of some material that has like a narrow distribution of pores centered at the let's say the other value, then the permeability wouldn't be that different. So it's got some influence, sometimes higher, sometimes smaller, but not. It wouldn't change the macroscopic form of the equations. That's the key message we had.
Thanks.
Hey, thanks for your question.
Thank you, Elena. Any other questions?
I have two small questions regarding the part of the talk when you showed the material with rotating elements of material in the start of your talk. Maybe I just didn't get it. Could you please tell what are the size of these elements? And did you experimental part or plan to do it? And so how it's possible to create this material to check it experimentally?
Yes, in particular, I think this was for this example was sub-millimetric size of this cylinder, but we have done some simulations for materials with larger cylinders, let's say about 4 centimeters. And what happens there is that this sort of peak goes down in frequency. So instead of having them, let's say, here in this example is about, let's say, nearly 2,000 hertz, but for let's say 4 centimeters, it's about let's say 50 hertz, 100 hertz. And it will be part of Claudio's PhD thesis to work out the experimental validation of this. So it's within our plans to do it. And how we will do it? Well, there are some ideas related to using, let's say, for example, cylinders with like a band that make them rotate in a different way, or use, let's say, magnetic means to rotate that, or directly connect them to these rotatory elements, like for example, Dremels, so that you can have like at least one cylinder that you can rotate. And with that, then we go on. We start with one cylinder, and then we make an array of them, so that we can have a better control of the experiment itself.
Thank you.
So we have some time for a couple of questions. Are there any? 1, 2, 3, no questions. Okay. Thank you. Thank you for the presentation. So I think the scientific part is done for today.